Thank you so much for joining us today, Professor Brian Cox.
Pleasure to be here.
So I last got to speak to you at the BBC London preview for the series Universe, and it's great to be speaking to you today about your new film, 7 Days on Mars, which is about your experiences at JPL following the Mars Perseverance rover as it makes its 7-day journey towards the Orotava crater. The first question I wanted to ask you is about kind of the star of the film itself, Mars Perseverance. I wanted to know how this rover has built on previous models that came before it, and why is it so much more sophisticated?
Yeah, it's an evolution in some ways, the Curiosity rover, which was very famously has been on Mars for a long time. But Perseverance is doing some things differently. One is that it's focused on taking samples from the Jezero crater, and in particular a dry river delta, which flowed into the crater maybe 3.84 billion years ago, because that is one of the places where we think life may have begun on Mars. So it's a sample, it's both analysing those samples and packaging them up to be returned to Earth, so it's part of what's called a sample return mission. But secondly, because it has to drive a long way, then it's got this autonomous driving capability. Basically, if you have to tell the rover what to do from Earth, and it will only do what you tell it to do, then it takes a long time to drive. You can't drive very far every day. But this rover can drive 200-300 meters a day, or even perhaps more. And that's really hard, because when you look at the pictures that come down from Perseverance, you don't really have a good impression of what obstacles there are 200-300 meters away. You imagine just sitting a camera on Earth and just taking some pictures and deciding to drive a rover, 300 meters away from where the camera is. If you look at the surface of Mars, it's strewn with not only boulders and rocks, but also sort of sand that the thing can get stuck in and all sorts of things. So what's different about Perseverance is that it can, when it gets a certain distance away from the site that it began its drive, then it can start making its own decisions. So it can, given some, and you see this in the documentary, given some kind of guidance, so that from orbital imagery and imagery on the ground, you'll say, well, don't go over there because that doesn't look very good, or don't go that way. But basically you can give it a point on Mars, which can be, as I said, many hundreds of meters away from where it is. And you can just say, go there. And if you don't have any problems and you don't get confused, then in the morning or whenever it is, when the signal comes back, usually it will have got there, but it will have plotted its own route. And that's absolutely unique. And what was interesting actually is that you see in the film, the capability to do that came in part from the processing power that it had to have in order to land, because it landed. It's the most difficult place by a long way that we've ever landed something on the surface of Mars. And the reason for that is because we want to look for signs of life. And so we wanted to go to somewhere that was an ancient lake bed with a river delta. And, because that's the most likely place. If you're going to guess, you think, well, maybe signs of life exist there. But that makes it difficult to land. It's a horrendous landing site. As you see in the film, that when the engineers say, when the scientists come and say, we'd like to go there, and you look at it, one of the engineers said, actually, all I saw when they showed me where they wanted to go was death, right? There are so many ways for this thing not to get there, and very few ways. So they had to have very complicated, because of the time delay between Earth and Mars, the rover has to land itself. It has to make its own decisions on the way down. You can't do anything about it. You're out of contact with it. Right? By the time you've got the signal back, say when it's floating down to the Martian surface, by the time the signals come back, it's already landed or not. Right? So it's got to do itself. It's got to make its own mind up. And it did, of course, and it successfully landed. But that computing power that was necessary to do that was then redeployable into an auto drive mode for the rover. So those are the things about it. It's a unique mission because it's a sample taking and return mission, and it's got unique capabilities because it can drive a long way on its own.
And speaking of that distance, actually, you mentioned at the start of the film that to make the distance it has to travel within the 7-day period, it's got to travel around about 200 meters a day. As you've just mentioned, and as we see in the film, there are so many things that can prevent them meeting that schedule. How difficult are these delays for the mission?
Well, they know that it's hard to do what they do. So a lot of running a mission like that is problem solving. And then so it's interesting when you speak to engineers at somewhere like JPL, they're relatively relaxed about problems occurring because it's built in. But one of them said, so one of the problems, it wasn't really a big issue, but they got a drill bit stuck in the rock. So the first day we were filming, the rover was taking a sample from a rock, and you don't know what that rock is, right? So you don't know the consistency of the rock, obviously, until you start drilling into it. And so they drilled in and it got stuck. Now that was a known thing. They knew that they would get drill bits stuck, and ultimately you can actually leave the drill bit behind. You can, but they don't want to do that because they haven't got many drill bits. And if you run out of drill bits, then you're not sending any more, right? So they have different ways. So they shake them around, and they, in the end, they realized they could break the rock sample off and take it. And that's all problem solving that you have to do, and then tell the rover to do things, and it will do it. So they know that everything isn't going to go to plan because it can't, because you're on the surface of an alien world millions of miles away. It's hard, right, to do. So and necessarily they are cautious. So they don't say, well, no, we really do want to go 250 meters today, so sod it. Let's have a go. You don't do that with a multi-billion-dollar rover on another planet. So they're cautious. So yeah, that's the thing that you learn. They're not. One of them said, again, one of the engineers said to me that before we got there, actually, they'd had a time where the sample, the way that they get the samples into the rover, because it takes them from the drill and then puts them inside the rover, and ultimately will go and get them and bring them back to Earth. And the way that it gets in is quite a complex mechanical thing. And they got a pebble stuck in it. Now obviously, it was designed so that you could get pebbles stuck in it, because the first thing you think of is what happens if a pebble gets stuck in this thing. But one of them said to me, it's one thing to go through all these meetings and design reviews on Earth and go, we've designed this thing so that if a pebble gets stuck, we can get the pebble out. Of course, you design it that way. But it's a whole other thing when it actually does get stuck on Mars. Then you go, oh, we better just not, we don't want to jam it up forever. I mean, if you jam the thing, you can't get the samples. So it was interesting to see how they problem solve when things they knew were going to happen and designed happen. And then, of course, they go back and go, well, okay, so let's just be really careful, obviously.
And this sample collection, it all ties into Perseverance's ultimate goal of looking for signs of past life. And one of the bits I really love in the film is how you mention how our expectation of what that life might be has dropped significantly since the 1930s. We've got a slightly more realistic idea of what we're likely to find now. And there are clues on Earth as to what that might be. But could you just talk about the kind of things that we might expect to find?
Yeah, so if you look at the history of life on Earth, then we have good evidence that life began here, let's say 3.8 billion years ago, with quite an error, but something like 3.8 billion years. That was single-celled life. And if you then look for evidence of anything more complex than a single cell on Earth, we don't have any evidence in the fossil record back beyond about, let's say, 600 million years or so, give or take. And there's a bit of genetic evidence that maybe the genes that code for multicellular organisms were present, but not more than 1 billion years. So it's very conservatively, let's say 1 billion years. So that means that on Earth, it took something like 3 billion years, as far as we can tell, to go from a single cell to something more complicated than a single cell. Now, on Mars, the conditions for life in Jezero crater, for example, the water there would not have been around for it's a few 100 million years at most, right? I think we're not talking about billions of years. So there wasn't much time. So if life began, then as far as anyone can guess, it would have stayed as a single cell. So we're talking about single-celled life at best on Mars. And that's hard. Some of the earliest evidence of life on Earth are things called stromatolites, which you find, for example, off the coast of Western Australia. And it took, one of the biologists said to me actually at JPL, that it was 20 years or so of arguments in scientific conferences around the world before those were accepted as being biological structures that were created by biology. Like decades, when we've actually got them, we can wade out into the sea off the coast of Western Australia and touch these things, right? And still, it took decades of argument to really pin down, because you're talking about structures which are no longer biology, right? They're just things that were made by the action of biology. That those things were biological in origin, even on Earth. So it's going to be a long process of looking at you have to characterize the environment, which is what Perseverance is doing. So it's going to do the geology on the surface. So you've got this context for the site. And then the samples have got to get back to Earth. And then you've got to look at them in Earth laboratories. And then probably you've got to have a load of scientists arguing for about 2 decades before you really, unless there's some kind of smoking gun there, which is probably not the way it's going to be.
Always seems to be the way. So I watched the film today, and I have to say by the end of it, I had one major burning question, which was that at the start of your career, did you ever imagine that you would one day be playing Interplanetary chicken with a Mars rover?
It's funny actually, isn't it? Because it's a really nice little sequence in the film but it has an element of Austin Powers about it. There's the big sort of a thing coming towards the guy really slowly, which is it's not only Austin Powers, it's almost in every Bond film, isn't it? You go, why just walk out of the way, just don't get into that situation. And it is true that you see that the rover obviously moves slowly and makes its decisions very carefully, and it's quite an imposing thing though. They're bigger. These rovers are bigger than you expect, actually. You don't really get a sense of it until you walk up to one and go, God, it's a big piece of equipment, this thing. However, it's moving towards you at 1 mile an hour or something at most, actually less, right? So it's not too hard if it makes a mistake to just wander off. You could literally crawl away from the thing, actually. Although it did crush one of our cameras, which was kind of sort of interesting.
I didn't. The watching Professor Brian Cox get run over by a Mars rover wasn't quite the sort of higher octane drama I had imagined. It was, definitely a gentler speed.
It is, but that's the remarkable thing though. You think about what it's doing. It is doing that itself. So and it's doing it. It's not like it's much harder than something like a self-driving car or something like. We're kind of used to these things in this technology now, but the thing is, on Mars, first of all, the stakes are higher, of course, because you're on Mars. So you're avoiding very small objects, and you're going across terrain that you didn't really understand before you got there. And also the electronics itself is difficult because it's got to be radiation hard. It's an extreme environment, so it's actually very difficult for a rover to do these things safely and reliably. So it's doing a lot with a very limited processing power. Actually, its processors are way less powerful than a phone. So because they have to be reliable and radiation hard and all that stuff. So it is actually it's a remarkable thing that it does it, but it takes its time. so you can get out of the way if you want.
Yeah, so as it's slowly trundling across the planet's surface, we're hoping that maybe we could be on the cusp of discovering that Mars did once have life. What I wanted to ask you is, do you think it could ever sustain life again, say, if we were to turn up?
Yeah, I think we will turn up at some point. When, I don't know. I would be surprised. Although we might start preparing in the next decade. So I think the way to do it probably is to start sending the infrastructure there first, even to the level of landers on the surface that can have the human habitation modules down there and make sure they're working. I think that's the way we'll do it. And that might commence within the next decade, but I don't think we'll be there until the 2040s. I think at the earliest is my guess, but I don't know. But I think, it depends what you mean by habitable. I mean, it's habitable. It's slightly more habitable than the moon, probably, in some ways, because there are more, the minerals there, and the water is probably more easily accessible on Mars. But it's a long way away, and it's still a hostile environment, and it's still, nasty radiation is a problem, all those things, because it's got no magnetic field. So, it's not going to be habitable in the way that Earth is habitable ever. You're going to be living in a bubble, basically, maybe in caves ultimately. Maybe that's the way to do it, build things, so you've got some kind of radiation shielding and stuff like that. It's hard to live on Mars. You don't want to, it's not going to be a tourist destination anytime soon.
I can imagine. So in the film, Ingenuity rightfully gets mentioned. And I wanted to ask you about why it was that the JPL team thought it was important that we also got these aerial views from a place where, as you mentioned, flying a helicopter should have been really difficult.
Yeah, it's Ingenuity. Initially, it was just an engineering test, really. I say just, it's a big deal, right, to fly a drone. It's basically a drone on the surface of Mars. That, because it has to do it itself, because so again, as with the rover, it has to make decisions. But the decisions are much more difficult to make when you're in the air. You can't trundle along like the rover does. And if it gets confused, the rover stops and waits. Well, a helicopter can't stop, right? So it's got to land. So once it's taken off, it's going to have to make a decision one way or the other how to get back down again. So, so they didn't think it was going to last very long, because it's got electronics in it that are far more intelligent than the rover, because it has to have, because it's flying. So they are mobile phone level intelligence, which is way above anything that's usually space qualified. So they thought it wouldn't last very long, but it has. And so it's become an integral part of the mission, which it wasn't really designed to be. So now it's mapping out terrain, it's taking a look at terrain the rover might go to, and they're hoping, if it survives, and it's way beyond its design life now, that it will be able to play a role when Perseverance is taking samples. It'll be able to be characterizing the environment around those samples with aerial photographs. So, I think some of the engineers said to me, now you start to think, well, we'll design that into future missions, that there'll be a drone component to them, because it's useful. But the problem is that in order to have the intelligence for a self-flying drone with very low power, very lightweight, you're talking about mobile phone technology, and it's not very robust, right? It's not good in a high radiation environment. We don't know really. We can't build intelligent enough electronics that light and with that low power in a way that you would if you said we are going to have a drone that will last on the surface of Mars for 1 year. Then we can't really do that. So, but we can build a drone with a couple of mobile phones running its brain, but they might die tomorrow because they're not hard, they're not hard, radiation hard electronic. So that was the thing with the helicopter, but it's still working as we speak, as far as I know. What are we now, the 10th of June? It's still going strong, which is astonishing.
Yeah, it's done an amazing job in surpassing everyone's expectations. So one of the key things that you mentioned as well in the film, as to why it is that we're on this hunt for life on Mars, is that river valleys showed that there were once these lakes, possibly even oceans, on the planet. I was wondering, is it possible that one day what we see on Mars could be what's left of Earth?
Yeah, ultimately, but by one day, we're really talking about the sun beginning to swell up and run out of fuel. So we're talking about, hundreds of millions, billions of years in the future. It's interesting also to look at Venus, though. So Venus, was also Earth-like. We have pretty good evidence, although less evidence than we have on Mars, that that there were oceans, and it was. And then what happened to Venus is runaway greenhouse effect. Now there are reasons why it was extreme. I mean, so it went from Earth-like to 450 degrees, 90 atmospheres pressure, absolute sort of hell planet, reasonably quickly. Well, in geological terms, but there's reasons for that. There's no plate tectonics, and it's different geologically to Earth. So every planet's different. So the thing you can say about Earth is it's remained stable enough for an unbroken chain of life for the best part of 4 billion years, which is possibly unusual. It may be probably unusual, actually. So that's why I think if you ask about complex living things and how far would you have to go out into a galaxy like the Milky Way to find something with complex living things on it, then I think the answer might be quite a long way. So you may have to go many thousands or even potentially hundreds of thousands of light years out to find something with an ecosystem as complex as that we find on Earth.
And for my final question, you're someone that's really taken science communication to the next level. I was wondering how important you think it is that achievements like this in fields like astronomy, that they're brought to the attention of everyone, not just those in the academic communities.
It's of overwhelming importance. I mean, that's one of the reasons, by the way, that NASA and JPL gave us access, because they take it extremely seriously. Because they take education and inspiration as seriously, I would say, as seriously as they do their science and their exploration, part of their mission. Because if you think about one of my heroes, Carl Sagan, said it beautifully. If you haven't read it, there's a great book called The Demon Haunted World, Science as a Candle in the Dark, which is one of Sagan's last books. And in there, he makes a powerful argument that the communication of science is in many ways as important as the science itself. Because if you think what science is, it's our way, the way of acquiring reliable knowledge about the natural world. So it's the way that we discover, and by reliable knowledge, I mean not only discovering whether there's life on Mars, or we go all the way back in history discovering that the Earth goes around the sun, or discovering how viruses work, or discovering how to develop vaccines to be topical, and so on. All those things require you to have a mechanism to acquire reliable knowledge about nature, and that is science. And our civilization rests on that, right? Like it or not, even if you're a person who doesn't, for some reason, like science, then you still use it. So our societies have to be set up, and the people in them have to just have a basic, if not understanding, then at least a recognition of the fact that this is the way that we interrogate nature, and the findings are to be taken seriously. Otherwise, your society doesn't work. And Sagan went as far as to argue that our democracies won't work if you lose the sense of a shared sort of reservoir of knowledge that you can all rely upon. It's not to say that no one is saying that we know everything, right? That's the point of science, right? Another great hero of mine, Richard Feynman, called science a satisfactory philosophy of ignorance. That's where its power lies, right? We start from the basic position that we know nothing at all, and then we try to acquire reliable knowledge. But if you lose that recognition that there is a shared reservoir of knowledge, then you basically lose the foundation of your civilization. It's that important. And actually, it's not only Sagan. If you go back to the 50s, another two people that I really hugely respect, big influences on me, Feynman, as I mentioned, Richard Feynman, also Robert Oppenheimer, actually, very interestingly. I'm working on academically now on black holes, and he did a lot of the early black hole research, actually. Then famously ran the Manhattan Project. So he was instrumental in developing the atomic bomb. And in the 50s, he thought very carefully about what he'd done. and the knowledge that he'd helped deliver to our civilization. He felt that our civilization did not have the wisdom to control that knowledge. And so the politics was running behind capability, which arguably it still is. And he thought, well, is there anything that we can do? You know, what is there anything that this tremendously successful enterprise, which we call science, that is there any transferable skill? Is there anything that it can tell us about the wider challenge of running our human societies? And he did come up with this view that it's the thing that science teaches you is humility. It's humility in the sense that you have to accept that you don't know everything, that there are things that we don't know how to do. And actually running society is one of them, which is why we have democracies, because you accept the fact that you don't know how to do it. So you change things every 4 or 5 years, right? That's central to it. So it's humility, but also perspective, and just the fact that there are things that we have to accept together as being a pool of knowledge that we have to respect. Otherwise, we can't make any progress. And so the communication of those ideas, the acquisition of the knowledge itself, because the knowledge is useless. If you have imagine that you have a civilization where, 70, 80, 90% of people do not respect the fact that there is a pool of knowledge that's been acquired reliably, then you have no civilization. So you can't acquire any more knowledge. So these two things are inextricably entwined.
Fantastic. And that's why it's so great that all of this knowledge is being brought to everyone in 7 Days on Mars. I know that all of our readers are going to love it as much as I did. So thank you so much for your time today. It's been great speaking to you again.
It's a pleasure. Nice to talk.